Alright, hello class. In this video we're going to be talking about working with integrals, or at least that's what the book calls this section. I would call this like an integration wrap-up. It's just sort of some miscellaneous things to talk about to round up and finish off talking about integrals, and really to finish off talking about Calculus 1. We're pretty much done with the semester, so we just have a couple more things to talk about. So let's not waste any time. Let's get right to it and get done with the class, right? All right, the first thing we're going to talk about is even and odd functions. And I think this is one of those things that it is something that we kind of forget about by the time we get to this point. And it's not actually that surprising because it's not something we really use that much until we get to integration. But here it's actually kind of useful because even and odd functions are symmetric, and we can use the symmetry of these functions to help us integrate quicker. Right, so this I would not say is something that is mandatory. Right, these are just techniques that can help you speed things up a little bit. And you'll be doing a lot of integrals, especially say in Calculus 2, so some of these techniques, kind of like flipping the integration limit with adding in a negative or renegating, this is sort of similar. It's a way that we can speed up our process a little bit. So what's the idea? Well, even functions are symmetric across the y-axis. Okay, so even functions, we define them in such a way that if we plug in a negative x, it's the same thing as plugging in a positive x for all x. Right? It basically crushes negatives. It gets rid of negatives. And you can think of that as even powers of x. Right? Even powers of x get rid of negatives. They are even functions. And they're symmetric about the y-axis. So if you think about functions like x squared, x to the fourth, 4 minus x squared, right? These functions are going to be symmetric about the y-axis. So x squared makes a u, x to the fourth makes a sort of broader u, 4 minus x squared, it's a parabola that just opens downwards. One I don't think many people think about, but that's cosine. Okay, cosine, it starts as trig function oscillating here at 1. But the idea of even functions is they are balanced. So the area, say on this side, is going to line up with the area on this side. So on different sides of the x-axis, you're going to have the same area. So this area, if we called it A1, will be the same as this area A1. So the total area, from this case, it would be negative 2 to 2. The integral from negative 2 to 2 of 4 minus x squared dx, that's the same thing as if we just took, say, the integral from 0 to 2 and multiplied it by 2, since we have symmetry. Okay, and that's the idea with even functions. If you're integrating even functions, right, if f of x is even, then if you're taking the definite integral over a balanced interval, so what I mean by a balanced interval is you're basically going from negative a to a, like negative 1 to 1, negative 2 to 2, negative 3 to 3, right, balanced. Then instead of doing that, you can instead just take the integral from 0 to a and multiply it by 2. Okay? And what's nice about that is if the lower limit is 0, well, that's always our nicest limit to plug in using the fundamental theorem of calculus. So just taking that and multiplying by 2 is great. That speeds up the process because we're not plugging in an f of a and an f of negative a. We're just plugging in an a and 0. And the reason why this works, oh well, again, it's because of the symmetry. Okay, on the other hand, odd functions. F is an odd function if when we plug in negative x, we can actually take out the negative. So if you can factor a negative out of a function completely and get back to the original, that's going to be an odd function. So you can think of odd powers of x, right? Because if you take negative x cubed, that's going to be negative x cubed, right? So x cubed is an odd function. Same with, say, x to the fifth, negative x to the fifth, we can take the negative outside. Sine is also an odd function, right? Sine of negative x is the same as sine of, or negative sine of x. Okay, and how these functions look is they are symmetric, what we call about the origin. And it means that if we have, say, a positive area on the positive side, we'll have the same value on the negative side, but flipped over, negative. Right? So we'll have a negative a and an a over here. Okay, that'll look exactly the same for x to the fifth. For sine, it, of course, starts at 0 and does its oscillations, but it does the exact opposite on the other side. So if this is a, this would be negative a. Okay, if we're talking about definite integrals. So because of that, even nicer with odd functions, right? If f is odd, then if we're taking an integral over a balanced interval, like negative 1 to 1, negative 2 to 2, etc., it's going to come out to be 0. Okay? It's going to cancel itself out, because we're going from, in this case it'd be, say, negative pi to pi for sine, you're just going to get 0. So this is even better, because if a function's odd and you're integrating over a nice balanced interval, 0. Okay? So when you have more and more integrals to calculate, if you see that the function you're looking at is odd and you're integrating over a balanced interval, you can just go straight to 0. Now, the problem, and it's not actually much of a problem, but most functions aren't even or odd. They're often a combination of one or the other, or they're neither. Okay, but we can still use these ideas to help us calculate definite integrals. Let me show you how that works. All right, so to show you what I mean, let's take a look at this negative, or integral from negative 2 to 2 of x to the fourth minus 3x cubed. Now, we could just, tackle this the long way, the normal way, right? So just integrate it directly. Integral of x to the fourth is 1/5 x to the fifth, and then we'll have negative 3/4 x to the fourth, and we'll just evaluate it from negative 2 to 2. Okay, so we plug in the 2 to get 1/5 times 2 to the fifth minus 3/4 times 2 to the fourth. Okay, so that's plugging in the 2, and then we plug in the negative 2 to get 1/5 times negative 2 to the fifth, okay, minus 3/4 times negative 2 to the fourth. So, as you can see, if we were able to rewrite this so we were going from 0, this part would just 0 out and we'd only be looking at this part. But on top of that, if we start just cranking things out, you'll start to see some balance happening, because 2 to the fifth is 32, so I have 32 fifths, minus, and here, this 2 to the fourth is 16, divided by 4, which will be 4, so this will be minus 12. Okay. And then here, we'll have minus, here this will be the same thing, but a negative, because the negative will come outside, right? The fifth power preserves negatives, so we'll have 32 fifths, but a negative. Then here we'll have minus 34, or 3/4, and then this to the fourth power will get rid of the negative, so we get negative 12 again. So when we distribute this negative, well, we'll have 32 fifths minus 12. When we distribute the negative, we'll get plus 32 fifths plus 12. So the 12s cancel, and we get double the 32 fifths. So 32 fifths times 2 or 64/5. Okay, now there's nothing wrong with doing it this way. However, notice the 32/5 part came from the even function, and we ended up with 2 of those, and the 12 came from this, which is an odd function, and they canceled out. So if we instead do it this way, right? If we think, oh, wait, okay, x to the 4th, that is an even function. And 3x cubed, that is an odd function. And we're on a balanced interval, -2 to 2, we could just split this up. We could say, all right, we want to instead look at the definite integral from -2 to 2 of x to the 4th dx minus the definite integral from -2 to 2 of 3x cubed dx. Okay? Now since this function is even, we could rewrite it as just 2 times the integral from 0 to 2 of x to the 4th dx. And then since this function is odd, we can just say that's 0, since we're on a balanced interval. And so now we're instead looking at just the definite integral from 0 to 2 of x to the 4th dx, and we'll just multiply by 2 at the end. Okay, so we'll get 2 times, we'll have 1/5 x to the 5th, and we'll evaluate this from 0 to 2, and so it will be 2/5 times 2 to the 5th minus 2/5 times 0 to the 5th. Right? So 2 to the 5th is 32, so this will be 64/5. We get the same thing. Is it more work, less work? The number of steps we have is pretty much the same. So some might argue by the fundamental, not the fundamental, but by the law of conservation of misery that it's, it's about the same amount of work. I would argue that though it's the same amount of steps, my brain processes this a lot easier than doing it the other way. Okay, so this really is just a method of, hey, let's make integrals faster to calculate. All right, to give another example of this, let's take the integral from -pi/2 to pi/2 of cosine x minus 4 sine cubed x dx. Now, what's nice about this is right off the top of my head, without some sort of crazy u substitution, this is, or using identities, this is actually kind of a difficult integral to do. However, sine cubed of x is odd, right? If we put -x into sine cubed x, well, that's sine of -x all cubed. And sine is odd, so this will be negative sine of x all cubed. And cubes preserve negatives, so we can actually take the negative all the way out to get negative sine of x all cubed, or negative sine cubed of x. So that means that this function right here is odd, and cosine is even. Okay? So we can actually just break this up like this. Take the negative, or definite integral from -pi/2 to pi/2, cosine of x dx, minus the definite integral from -pi/2 to pi/2 of this 4 sine cubed x dx. The beautiful thing here is this whole thing just goes to 0. And this we can rewrite as 2 times the integral from 0 to pi/2 cosine x dx. Much easier problem here than this one, right? Because the integral of cosine x is 2 sine x. Well, I have a 2 there. And we'll evaluate this from pi/2 to 0. Right? So it'll be 2 sine of pi/2 minus 2 sine of 0. So sine of pi/2 is 1, so this will be 2 minus 0, or 2. There we go. All right, so let's talk about the average value of a function. Now we kind of know how an average works in general. When we take the average of a list of things, it's going to be like the first thing plus the second thing plus the third thing, all the way up to however many things you have, and you divide by that many things. Right? That's how you get your average. Well, it turns out we can actually do this for functions over an interval a to b, right? And we can do so using integration. So how we do that is if we have the interval, say a to b, and we say take n values of f, right? So we take like, maybe it'd be n plus 1, so we'll have x naught, x1, x2, all the way up to xn. Right, we can take the average. Okay, so we can take the average of the f values over these n x values. So the average of the f of xn's is basically we sum them up. So we have f of, let's say, x1, x2, all the way up to f of xn, and then we divide them by the value n. Now, maybe this looks familiar, right? In fact, if we remember that delta x here, if we do this in the same way that we do our usual integrals, our delta x is b minus a over n. And if we solve this for n, right, we basically move this over to get n is equal to b minus a over delta x. Replacing this n here with this b minus a over delta x, we get, so the average of n values, okay, will end up being this sum. So let me write it like this. The sum k going from 1 to n of f of x sub n all over b minus a over n. Oops, sorry, over delta x. Okay. When we invert and multiply, we're going to get delta x times the sum k going from 1 to n of f of x sub n all over b minus a. Okay, or a nicer way to write it would be 1 over b minus a times delta x times the sum k going from 1 to n of f of x sub n. Now, this is the average over n elements. Okay? If we want the average over the entire interval, over all of a to b, right, every single point in a to b, we would essentially take the limit as n goes to infinity. We would take infinite number of values, all the values between a and b of this thing we have here. Okay, and as we discussed before, well, this 1 over b minus a, that's not being affected. This is the integral when we take that limit, right? So this is going to be 1 over b minus a times the integral from a to b of f of x dx. Okay, so that's the average value of f on a to b, and this is often notated as f bar. At least that's what the book uses. Okay, so that's basically, if you take the definite integral of a function over an interval and divide by the length of that interval, that's the average value of f overall. All right, now there's some neat things we can actually do with this. So let's look at an example, and I'll show you kind of graphically what this gives us. Okay, but first let me just sort of clean this up a little bit, give you a nicer thing to refer back to in your notes. All right, so the average value of f of x over a to b is given by this. F bar is 1 over b minus a times the definite integral from a to b of f of x dx. All right, so let's look at a quick example. Let's find the average value of f of x equals x squared plus 1 on the interval -1 to 1. Okay, so just based on the formula, f bar will be 1 over b minus a, so that will be 1 minus -1, right, times the definite integral from -1 to 1 of x squared plus 1 dx. Okay, so this is going to be so 1/2. However, this is an even function, right? F of negative x is negative x all squared plus 1, which is x squared plus 1. So this is an even function. So this will be 1/2 times the definite integral from -1 to 1 of x squared plus 1 dx. However, we can rewrite that as 1/2 times 2 times the definite integral from 0 to 1 of x squared plus 1 dx. Again, you don't have to do that, but that will make our work a little nicer. So really, it's just going to be the definite integral from 0 to 1 of x squared plus 1 dx. Okay, so here's what we get. When we take the antiderivative, we'll get 1/3 x cubed plus x evaluated from 0 to 1. All right, so plugging in the 1, we'll get 1/3 times 1 cubed, which is 1, plus 1, minus 0 plus 0. All right, so 1/3 plus 3/3 is 4/3. So that is the average value. Okay, now here's what I want to show here. All right, so now what I want to show is geometrically what this means, because what's interesting about this is if the average value of f is 1 over b minus a, right, times the integral from a to b of f of x dx, what this basically means is if we move this over and have f bar times b minus a, that's equal to the definite integral, right, of f of x dx from a to b. This is actually a rectangle with height f bar and base basically our full interval, right? So this ends up being the area of a rectangle made by the average value and the full interval. And it turns out to be actually equal to the area beneath the curve of f, okay? Which actually ends up being sort of an interesting idea here. So if we look at the graph, so here is x squared plus 1, and then here is the actual integral from -1 to 1, and I had the software calculate it. It's about 2.6 repeating. It is 2.6 repeating, okay? Now, here is the average value, right? Let me make that a little brighter, okay? Here's the average value. This is 4/3, okay? Now, if I set up an integral from -1 to 1 of just 4/3, right? If I just look at the area of the rectangle, we end up getting the same area out with this rectangle, okay? So it turns out that the area beneath the curve itself matches the rectangle made with the average height. Okay, they come out to be the same. So that's just an interesting geometric property of this. Okay, of course, there's also just the fact that this can give us, say, the average height or the average velocity or the average temperature of any sort of quantity that we're studying at the time. All right, to give an example of this, let's say the height of an arch above the ground is given by this function. H of x is 10 sine x for x between 0 and pi. Right, so what is the average height of the arch arch above the ground. Okay, well, h bar is going to be 1 over b minus a, so that's going to be pi minus 0 times the integral from 0 to pi of 10 sine x dx. All right, so now this will be 1 over pi times the integral of 10 sine x is going to be negative 10 cosine x. We're going to evaluate that between 0 and pi. Now you might think that doesn't make sense to have an average height be negative. However, when you plug in pi, you're going to get negative 1. Okay, so we're going to get 1 over pi times, all right, we'll plug in the pi, so we'll get negative 10 times cosine of pi minus a negative 10 cosine of 0. Now, don't be so quick to jump to making this 0. Remember, cosine of 0 is 1. So cosine of 0 is 1, and cosine of pi is negative 1. So we're going to have 1 over pi times negative 10 times negative 1. So we'll have 10 minus, and that'll be a negative, negative, so plus 10. And so this is going to be 20 over pi. All right, and to show graphically, here is the function itself, 10 sine x. You see it makes this arch, and its maximum height here is at 10. However, its average height is here at 20 over pi, and what that's basically telling us is that the area beneath this curve is the same thing as the area of this rectangle with height equal to its average value, or its average height. Okay? All right, and that pretty much rounds it up. That is really all there is left to talk about as far as this wrap-up of integration techniques. So that should get you rolling on the homework for this section, and that is it for this class. Thank you all very much, and I hope you, I wish you good luck in your future classes and finishing up this one. All right, cheers, folks.